We'll list some of the exceptions here. You probably already know one of them. Hydrogen. What's its octet? This is why I got octet in quotes. We're looking at 2 electrons because it's all it can handle in its s orbital. Boron and aluminum. They're an interesting pair. And again, depending on how we look at the structures, we can come up with different options. What's their octet in quotes? 6. Okay. The next one that we're going to run into is n greater than or equal to 3. What element is n greater than or equal to 3? What does the n mean? You guys remember your quantum numbers, right? From 151? Everybody, oh man, the spacing is horrible. It's our energy level, which means ultimately our rho on our periodic table. Okay, rho pt. Where's sulfur? 3rd row. What can sulfur do? It can expand its octet. Which means, not only do we have some exceptions where we have less than 8 electrons, but we also have exceptions where we can put in more than 8 electrons. But if we look at that 2nd row again, why can we not expand the octet? Why can we not go above 8 electrons? What orbitals are available to us in that 2nd row? The s and the p. There are no other orbitals. What happens when we move to n equals 3? Our quantum number L, I think it's L, is 0, 1, and 2. 0 was S, 1 was P, 2 is D. As soon as we hit that 3rd energy level, we now have the d orbitals available. So sulfur and phosphorus can expand their octet because they have empty d orbitals. So we can start shuttling electrons into those to help us expand that octet to a larger than 8 amount. Which is our explanation for why we can jump up to the example shown here, okay, with sulfate, with the 2 double bonds. Okay. The question now becomes is why? When do we know to expand the octet? When do we not expand the octet? Okay, and that's a much more challenging question. Okay, to answer that, you have to have a proper rule set to follow when you go through and build Lewis structures. Every instructor I've seen has a slightly different rule set. That said, of course, I think mine is the best. Okay? This is a lot of words up here and a lot of individual rules, but it consistently works and it allows you to get at certain aspects that other rule sets don't. For instance, resonance, massively important for organic chemistry, and expanded octets. Okay? So the first set of rules are all pretty much the same. You need to total the number of valence electrons available. So you'll go through and count every single atom and look at their valence electrons. So I know this is going to kind of suck for a recording because I'm going to draw it up on the board, but that's the way it's going to work. Shouldn't have erased that. Oh well. So if we take a look at SO4 minus 2, we total our valence. How many valence electrons does sulfur have? 6. How do you know it has 6? It's in that 6th column over. Oxygen has 6. How many oxygens are there? Right? We can do all the addition, or we can multiply it out. We also have a -2 charge. What does that mean?
Add 2 more electrons.
We have to add 2 more electrons. Why do we add them to it? What charge is an electron? Negative. The only way we become negatively charged is if we added those electrons in. We should end up with 32. I can't count. I'll trust you guys. 32. Okay. 30. Tell me it's 34 now? Okay, 32. Choose a central atom to act as your connector or bridge. Okay, that becomes a little bit tricky. It's usually the least electronegative element, but if we picked a compound like CH4, Is hydrogen, being the least electronegative atom, our center atom? No, because it cannot bridge. You have to link to at least 2 other atoms, okay, to be our bridge. So sulfur's in the middle. We'll scatter our other atoms around it. All right, now what do we do? Again, where I differ from most rule sets. We're going to add electrons to this structure in pairs, okay, because each orbital can hold 2 electrons, a pair. Where am I going to start putting those electrons?
Around the central atom.
What does my rule set say? The most electronegative atom. Why?
They're going to attract the electron more.
Because?
They're going to like grab the electrons more than the other
Why are they going to grab the electrons more than the other one? I know it's a redundant definition, but that's exactly what I want.
one. More electronegative.
They're more electronegative. So I want to put the electrons where they're most likely to go within the structure. So I'll start putting them in pairs until what?
To fill the octet.
Until I satisfy my octet, which for oxygen is
It's 8.
8 electrons. How many electrons do I have drawn? 32. What's my next rule? Pairs of electrons between atoms. Is this electron between an atom?
No.
No. These pairs are. I now have a bond. Why do I use a line to represent a bond? Because I don't want it to look like a pair of electrons. We use the line to represent a bond, not a pair of electrons, because that way it looks different. Okay? There are some rule sets that every pair turns into a line, but then I get lines floating everywhere and I have no idea what's a bond and what's not a bond. Okay? Next rule set. Use non-bonding pairs of electrons to atoms that have not satisfied their octet. Okay? Well, our octet is always 8 electrons. Okay? Do any of our atoms not have 8 electrons around them? No, they all have 8 electrons, so we're good. Okay? So we don't have to move any electrons. We don't even have to look at resonance because there's no reason to move electrons. We can then go through and assign all non-zero formal charges. How do you assign formal charge? I know you all remember this one, right?
A valence electron minus the
Actual amount of
the one in ohms.
Ohms, that's a lovely word. Personally, I hate that word because to know what ohms means, you have to know some more mumbo-jumbo associated with it. So let's try it a different way. Valence electrons minus bonds. Not even electrons, bonds.
Minus half of the electrons in bonds.
That half is exactly one of the reasons why I think that old method is a load of crap. How many of you are comfortable with fractions? Yeah, that was 3 hands. Why did we bring a half in there? If we just count the number of bonds, we're solid. Okay? We don't have to count half the number of electrons in bonds. Why do we do that? 151 and 152 are concerned about one thing and one thing only. And I know this comes as a surprise. Units. Nothing else taught in 151 or 152 did anything beyond units. Everything was units. So if we gave you a formula that said electrons minus bonds, the pioneering student would be the units don't match. I don't care about units. This is not 151 or 152. Count the number of bonds. Okay? Minus the number of non-bonding electrons. Another thing that gets different with how I'm defining this as opposed to how you'll typically see in a book. They almost always say the number of lone pair electrons. So let's go through, let's pick oxygen. How many valence electrons does oxygen have? 6. Minus the number of bonds. Let's pick this oxygen. How many bonds does it have? 1. Minus the number of non-bonding electrons. How many electrons are not in bonds? What if I'd said minus the number of electron or lone pair electrons? You might have a tendency to say 3 because stupid word pair. Okay, we're looking at the number of electrons. What's our result? -1. What's the charge on oxygen?
-1.
-1. So we can assign a formal charge to that atom. We can go through and do it with every other atom. You'll notice all of the oxygens will come out as a -1. Right away, you should start to be a little panicked because the charge on the molecule was -2, and I currently have 4 minuses. What else do we find? The sulfur is
This is a +2.
a +2. Okay? That is officially your Lewis structure. Lewis looked at this structure and said, everything wants to strive for neutrality. What's the problem with this structure? It's not neutral. It starts not neutral. It starts as a -2. So expecting to see it go neutral is a bit much. But we would want to minimize that charge as much as possible. So what did Lewis go through and say? What happens if I have a positive and I put a negative near it?
Cancel.
They cancel. So what do is we go back to Rule 6. And what we're going to do is tweak Rule 6 to, instead of satisfying octets, we're just going to try and remove charge. Okay? What do we move when we look at organic chemistry? Electrons. So what we'll do is find a charge, or a non-bonding pair of electrons, and move them towards another atom to neutralize charge. So if I take these electrons and I now put them on sulfur, sulfur's charge becomes more neutral. But what happens to the oxygen? Does it have its octet? No, that's a problem. So instead of just picking up and moving the electrons, I'm going to share the electrons. Okay? I now form that double bond. When we go through and now recalculate the formal charge, 6 minus 2 minus 4 gets us 0. There is no formal charge. Okay? The sulfur, if I recalculate, becomes +1. I've neutralized some of the charge. This is pretty awesome. Okay? So let's see if we can keep doing it. Turns out we can. And we end up with our generally accepted structure for the sulfate anion. Okay. How did we jump to that double bond structure? Well, we had to have a rule set to follow. That has to do with this extra thing beyond formal charge. Balancing that charge, trying to make our structure as neutral as possible. The more neutral our structure, the better the Lewis structure. Okay. Which brings up another point too, resonance. The reason resonance showed up was to balance an octet. Right? Useful to balance octets. Does resonance show up here as well? Did I have to take the electrons from that oxygen or that oxygen? No, I could have taken it from this oxygen or this oxygen. If there is a different source of electrons that I could have moved, I now have resonance. Why does that become exceptionally obnoxious with sulfate? There's a lot of resonance. So if asked on an exam, which of these structures is correct? This is a favorite question that people love to hear. It's a little bit worse than they're both correct. They're all correct, which means if you give me one, you're wrong. Because that's only part of the answer. Resonance represents all of the structures that are of equal energy to get to that same compound. That said, I would never ask sulfate, because there's a lot of resonance with it. Okay? But is that something that you need to be looking for and tracking? Yes. Every time you draw a Lewis structure, you should be thinking about this concept of resonance. Okay? It does not matter what rule set you decide to go through and follow. However, if you do talk to me about drawing a structure, okay, particularly the simple ones where we can follow these rules, okay, I will ask you to follow that rule set or explain your rule set to me. Okay? One of the ones that is my least favorite, and I hear this all the time in the tutoring center, and it gives me anger bumps, I don't know. Okay? People go through and say, this is the correct structure because sulfur has 6 valence electrons and it has 6 bonds. So you mean you saw some random connection that has absolutely nothing to do with the chemistry associated with the molecule and you said that was the answer? Cool, I can make stuff up too. Okay? We need a rule set to understand why these things occur. Okay? Getting the answer on an exam, do whatever you got to do. Okay? Short of cheating. If you're cheating, that's a problem. Okay? But when it comes to trying to work the problems, I'm going to try and make you go through these individual steps and understand why these things are happening. Remember, the stuff builds as we go. So if you don't understand why, it comes to second semester, and I say, well, how many electrons are around oxygen? You tell me 6. I'm going to flip out, because there aren't 6 electrons around oxygen. How many electrons are around this oxygen? 8, because of the bonds. Okay? Kind of makes sense? Lewis structures is kind of a thing of mine, I guess. Okay? So, how do you go through and set up Lewis structures where you can consistently be good at this? It's practice. It's tons and tons of practice. So typically what happens within that first chapter is we throw 50 Lewis structure problems at you, all relatively simple, okay, where you have one center atom, CO2, carbon monoxide, carbonate ion. We give you those, and you just start crunching them out, and you start to pick up patterns. Those patterns are carbon has 4 bonds, boron's happy at 3, nitrogen's got 3 bonds and a lone pair, oxygen's got 2 bonds and 2 lone pairs. This is summarized later. You don't have to just write that all down. Okay? So you pick up these patterns on what different atoms do. And remember, we only have 10 atoms to worry about. Okay? And once we have those patterns down, we can start to quickly draw structures out. Which brings up our last case of being problematic, C3H8O. That is a formula. And arguably one of the only organic compounds on that list. But if you try and draw out that formula, you will probably find that multiple people will get different answers. Because there's a bunch of different ways you could connect those atoms. Okay? All of them are equally valid. So we talk about all this effort in Lewis structures and trying to get you to think about how to connect these atoms, when ultimately at the very end of this we're going to say formulas are useless. We don't want you to draw formulas, we want you to interpret structures. Okay? So all those formulas that are nice and simple and neat and you can put in a single line very rarely show up, and we'll go moving towards structures. Okay? And structures are going to drive everything that we go through and look at. So we have to be careful with how we approach these things. You guys want to take a crack at C3H8O and see what you can come up with? Okay. I'll give you a couple minutes to take a swing at it. This one.
All right, you can do that one.
So when we go through and look at drawing structures from formulas, you'll notice that this formula works. 3 carbons, 8 hydrogens, 1 oxygen. At least in my cursory look around the room, nobody had it. This is why formulas suck. Okay? What we've got to do is come up with some way to connect these atoms as independent pieces and see what we can come up with when we go through and process these. What we're looking at is that that individual compound has, I believe, 3 isomers, which is a fancy way of saying different ways of drawing the structure. Trying to think if there's any others, and I think that's it. Okay. What functional group do we have here? I know I just threw that at you. It's an ether. We have an oxygen embedded between carbons. The functional group that most people drew was, just look at what you draw, or what you drew. What did you draw? You drew an alcohol. Okay. Most people drew propanol. So 3 carbons in a chain, and the oxygen coming off one of the either starting or ending carbons. The other option is to draw 2 propanol, meaning your alcohol, that oxygen was coming off of the second carbon. Comes in nomenclature. You're not responsible for nomenclature yet, but it's not a bad thing to start reviewing. The book has nice segmented chapters or sections on nomenclature. Okay? Questions with that? Okay, because resonance is going to pop up here. I kind of want to talk about it. Okay? Particularly in second semester. So if you decide to not take second semester with me, or even if you do, realize if you're ever asked the question, why did it do that? Why did it react that way? About 70% of the time, the answer is resonance. So just memorize that, because 70% of the time, you'll be right. It's a pretty awesome deal. Okay? So resonance is the ability to rearrange a structure's electrons, and only the electrons, in more than one way. Okay? We do also have this equal energy caveat, which pops into it. Okay? So the question then becomes is, well, what electrons can we move? Any ideas? As a hint, if we were going to draw this structure out, when we dealt with our sulfate, we formed double bonds, right? What if we did the reverse of that? All right, so let's take the double bond and move it back to our oxygen. So we'll start our arrow at our double bond, and we move the electrons up. How many electrons are in a single line? 2, which means when we draw the structure out, what do we end up with? Calling it 6 electrons makes me nervous. 6 non-bonding electrons are on that top oxygen. We'd have this structure. I don't care about formal charges right now. Okay, so we'll ignore that for the moment. So we can take a double bond. Okay, only one double bond. Okay, the other thing that we could go through and do is move those electrons. But then the question is, how do we move them? Would I have moved them towards the carbon? Why not? Electronegativity. Electronegativity plays an important role in this class. Okay? Oxygen is more electronegative than carbon. The electrons are going to be drawn towards the more electronegative element. It does not make sense to have the electrons come back to the carbon. We'll send them out to that oxygen. Why not take those electrons and move them to one of the other oxygens? Why is that a horrible, horrible, horrible thing to do? Remember the whole fork in the outlet? What's coming out of the outlet? Electrons. Electrons are insanely unstable, which is why we don't stick forks in outlets, because we don't want to be that close to them. However, are we really concerned about them right now? A couple of you are sitting right next to this dangerous source of electricity. Why are you not freaking out? Okay, you're too far away. There's a distance that separates you. That distance, when we're looking at our electrons, can only move from a bond to an atom or from an atom to a bond. And it's the immediate proximal distance. We cannot jump through multiple atoms or multiple bonds. Okay? So they will move to our more electronegative. Our other option is we can then move our electrons. Sorry, I'm going to talk through this one really fast because we are done. Over across. And we could end up with our new structure. I know you all will tell me that this looks exactly the same. All I did was rotate the compound. When we deal with resonance, you cannot pick up, rotate, or spin the molecule. It is frozen in place, like one of those frogs that you pin down in anatomy class or biology class. Cannot move. Okay? Which means the structure on the right is inherently different than the structure on the left. One other option that we can go through and do, we strung this through kind of an intermediate structure in red. Could I jump from my black structure to my purple structure in one fell swoop? I'm going to attempt to move electrons from that bottom right oxygen to forming a double bond with the carbon. How many electrons are around that carbon? Too many. Octet is invalidated. So before I can draw that, I have to fix that. How do I fix that? I'll add a second arrow into my structure. I have now jumped through my orange system all the way across. So we got 3 ways to go ahead and draw our resonance arrows. We can go from an atom to a bond, or a bond to an atom. Or a bond to an atom. Okay? Questions? We're done. We'll pick it up there.